Okay, I'm audible now. Hello, hello.
Yes, sir. Yes, sir.
Oh, okay, fine. Uh, Maybe those who are not submitted the assignment submit as quickly as possible. Right. And I will start one more chapter, but the unit is same. Heterocyclic and carbohydrate unit is same, but only the two chapter. One is heterocyclic, another one is carbohydrate. So I think you are aware about what is carbohydrate. So initially, scientists they are under the impression that carbohydrates are nothing but a carbon and hydrogen containing compounds. They also given a general structural formula of carbohydrate as CH2OY. So that means X times carbon, Y times water. So this general, let's give an entry. Okay. This CH2OY, so this is applicable to certain carbohydrates, for example, glucose. So when you are taking a C6H12O6, C6, this C6H12O6 can be written as C6H2O whole twice 6 numbers. So that means the general formula is applicable for glucose. Similarly, so when you are taking a sucrose means a disaccharide, C12H22O11, here oxygen O11 is there. So that we can write it as a C12H2O twice 11 times. So that means the general formula is applicable for glucose as well as sucrose. Let's go to the next slide. Okay, let's give an entry. Right. Here, but this definition has certain drawbacks. So definition means carbohydrates are nothing but a carbon and water containing compounds. Otherwise, carbon and hydrogen containing compounds, that is having a drawback because so the whatever the general formula, so it is also applicable to HCHO. What is HCHO? It's a formaldehyde. How formaldehyde we can write? CH2O twice, one time. Here n is equal, here x is equal to 1, y is equal to 1. So then you know that formaldehyde is not a carbohydrate. In the sense, it's not a carbohydrate. Of course, it contains carbon and oxygen, carbon and hydrogen. So similarly, if we are taking a acetic acid, how we can write acetic acid? C2H2O twice. This is also a obese carbohydrate general formula. So acetic acid, it's not a carbohydrate. Similarly, so one more. So there are carbohydrate. They contain nitrogen as the element. There are carbohydrate. They contain sulfur as the element. So that is the reason. So based on all these factors, the carbohydrates definition was reintroduced, and as per the definition reintroduced definition, the carbohydrates are polyhydroxyaldehyde carbohydrates or polyhydroxyaldehyde or ketones and contain at least one chiral carbon atom. Okay, contain at least one chiral carbon atom. So that means carbohydrates are the polyhydroxyaldehyde or ketone and they at least contain one chiral carbon atom. Then such compounds are called carbohydrates. Right. Is it clear? Is there any doubt up to this? Any doubt up to this? Hello? Am I audible? Okay. Is there any doubt up to this? Okay.
Explain once again, sir.
Oh, right. So carbohydrate means initially the scientists were they are under the impression that the carbohydrates are nothing but a carbon and hydrogen containing compounds. So some they used to say that carbohydrates are nothing but a hydrates of carbon, hydrates of carbon. So they have also given a general formula CxH2OY. This CxH2OY, it is applicable to the glucose, sucrose. Okay, glucose, what is the general formula? C6H12O6. So this we can write it as a C6H2O 6 times. So it is applicable. Sucrose, C12H22O11. So this we can rearrange and we can write a C12H2O twice means over 11. So this also a applicable as per the general formula. I will go to the next slide. So here I am taking few examples. For example, formaldehyde and acetic acid. So formaldehyde and acetic acid, they are not the carbohydrate, but the formaldehyde and acetic acid, you can write it in the form of hydrates of carbon. So that is the reason the general formula was not the correct one, which is initially given for the carbohydrate as hydrates of carbon. And one more thing, so there are carbohydrates. So certain carbohydrate contains nitrogen and sulfur in it. So for example, chitin, it's a naturally occurring compound. It contains nitrogen element and it is a carbohydrate. Similarly, so the again one more amino acid that means carbohydrate contains sulfur as the heteroatom. So in order to in order to overcome these problems, a new definition was given. So as per the new definition for carbohydrate, so carbohydrates are nothing but a polyhydroxyaldehyde or polyhydroxyketone and they contain at least one chiral carbon atom and these type of compounds are called carbohydrates. With this, I will go to the next slide. So I think you are aware about, more particularly in the next slide, I am talking about the classification. Okay, so I think you are aware about monomer, dimer. So similarly, monosaccharides and disaccharides. So glucose is the example of monosaccharides, sucrose is the example of disaccharides. Similarly, one more terminology I will use in the next slide onwards, that is triose. And if you are looking into the classification of sugars or carbohydrates, so these are classified into reducing sugars and non-reducing sugars, and also they are also classified as posozones. So classification of carbohydrate means reducing sugars, non-reducing sugars, reducing sugars and non-reducing sugars. So reducing sugar means the one if the aldehyde group, if the aldehyde group is free, that can be reduced. If there is no free means it will act as a non-reducing sugar. If the aldehyde group is free, that will act as a reducing sugar. And another type of classification of carbohydrates are posozones. So now let's give an heading called determination of configuration of monosaccharides. Again, monosaccharides means, for example, only one unit. Okay, so for example, these are the compounds which cannot be hydrolyzed further. So whereas the disaccharides and polysaccharides, so which on hydrolysis gives monosaccharides as the product. So monosaccharides are the carbohydrates which cannot be further hydrolyzed. And again, under the monosaccharides, I will take up different one. See, for example, aldose. So what it means, aldo? Aldo means a aldehyde containing one. Trioses means tri indicates the number of carbon atom present in it. OSC is the general suffix for the carbohydrate. So aldo stands for aldehyde, tri stands for 3 number of carbon atom, OSC stands for carbohydrate. So here I am taking two examples. So tell me, both are same or different? So this D plus
difference in hydroxyl group.
Difference in hydroxyl group.
Sir. In first structure it is present in right side, so it is deglyceraldase. In second structure it is present in the
Mirror
left.
images.
Very good, very good, very good. Okay, both are definitely a mirror images to each other. So if the mirror images to each other, then we can say that enantiomers, isn't it?
Yes, sir.
So enantiomers are the non-superimposable mirror images to each other. Of course, D glyceraldehyde and L glyceraldehyde are the mirror enantiomers, and they are non-superimposable mirror images to each other. So another thing we can say that both are having the same molecular formula, but they will have a different structure. More particularly, here what you can observe, a hydroxy group, so which is on the right hand side, it's called D. D stands here in this, D stands for dextro. Okay, it is not related to experimental phenomena called optical rotation. So usually plus stands for optical rotation. So plus or minus indicates the rotation of the optical rotation of a given optically active compound. So whereas the D, it's a theoretical phenomena. So D is assigned to the optically active compound, the particular optically active compound if the highest priority group is on the right hand side, then it is called D. Similarly, in a optically active compound, if the highest priority group is on the left hand side, then it's called L. So in L also, it's a theoretical phenomena, but not the experimental one. Here, experimental one is minus. Minus, what it indicates? Minus is a levorotatory. Levo means this particular compound rotates the plane polarized light uh, uh, towards the left. Okay, that's what the minus indicates. Okay, so here and this D-glyceraldehyde and L-glyceraldehyde, initially scientists taken as a arbitrary standard for optically active compounds, because in olden times, so this was the only compound known as optically active compound, and this itself they are taken as arbitrary standard for the optically active compound, and later on, so this configuration is confirmed, and then they are said about absolute configuration. So you need to remember that aldose means it's a glyceraldehyde. More particularly, D plus glyceraldehyde and L minus glyceraldehyde. D and L is a theoretical phenomena which is assigned based on the highest priority group. If the highest priority group is on the right hand side, then it's called D. If the highest priority group is on the left hand side, then it's called L. And plus and minus is the experimental phenomena. So this plus and minus is assigned based on the experiment called plane polarized light. If the plane polarized light rotates towards the right, then it's called dextro. If the plane polarized light rotates the molecule towards left, then it's called minus. And of course, this is the name of this compound, glyceraldehyde. So this also a name of this compound, glyceraldehyde. And one more thing, here note you need to remember, so D can be plus, D can be minus, because D is a theoretical phenomena, plus and minus is the experimental phenomena. This plus and minus depends on the compound's plane polarized light rotation, optical rotation. Plus and minus is nothing but a optical rotation. So this is about what is called as aldotrioses. Now tell me, glyceraldehyde is a monosaccharide or not? One minute. Okay. Hello. Okay, tell me, glyceraldehyde is a monosaccharide or not?
Yes, sir, it is monosaccharide.
Okay, more particularly, it is aldotriose. So here aldo indicates aldehyde, tri indicates 3-carbon atom, OSC indicates carbohydrate. So I will go for the next category. Next category means if we are adding one more carbon to the trioses, then what we can say that aldotetroses. So aldotetroses. Here aldo indicates a aldehyde group, a tetroses, otherwise tetra indicates 4-carbon atom. 1, 2, 3, 4. And OSC indicates it's a carbohydrate. And what you can observe here, so this is one optically active compound. This is also one more optically active compound. So that means aldotriose contains only one optically active compound. Aldotetrose contains 2 optically active compounds. This will be the general structure of aldotriose. tetroses. And you can observe that there are 2 chiral carbon atoms. And you know that by using a formula, we can calculate the number of isomers present in it. So what is the formula? 2 to the power of n. So here n is equal to number of chiral carbon atom. You know that 2 chiral carbon atom. So 2 to the power of 2, that is equal to 4. So that means 4 optically active isomers are possible, and all of 4 isomers are known, and this corresponds to D and L isomers of erythrose and triose. So now in this slide you need to learn what is erythrose, what is triose. Okay. So in order to look for a tetrose, so let's start with the triose. So what is the name of the compound? It's a D-glyceraldehyde. So more particularly, why it is D? Because the hydroxy group is on the right hand side. So this D-glyceraldehyde, when it is subjected to Kiliani synthesis. So what is Kiliani synthesis? Kiliani synthesis is nothing but a reaction of an aldehyde with hydrogen cyanide. Okay. So what it means? It undergoes addition reaction. So what it means? It means that HCN will add to aldehyde. So when HCN is adding to aldehyde, aldehyde is converted into alcohol and nitrile group. So the Kiliani synthesis involves 2 or 3 a multi-step reaction. So here a aldehyde is treated with hydrogen cyanide, and the obtained nitrile subjected to hydrolysis followed by reduction. So that means a glyceraldehyde, when it is treated with HCN, a cyanohydrin, CN will add here. Okay, C double bond O aldehyde is converted into OH, and the obtained CN nitrile, so which was hydrolyzed to get a carboxylic acid, and that is esterified and then reduced to aldehyde. So what is the difference between a glyceraldehyde and erythrose? So here erythrose means erythro indicates that the priority groups. So OH, priority groups are on the same side. Erythro means priority groups are on the same side. And here, from here to here, 1 carbon is more. And from here to here, this aldehyde CHO is converted into OH. And this CHO is newly introduced. So newly introduced by Kiliani synthesis. And what is the difference between erythrose and triose? So only, I think you are aware about what is called as, okay.
They are diastereomers.
Very good. So they are, both are erythrose and triose are the diastereomers. That's fine.
Yes.
Because it contains 2 chiral carbon atoms. So what I mean, what I am asking, so just I am asking the difference between the erythrose and the triose. Of course, these 2 are diastereomers. What I want to make it clear, you just can observe this is the carbon atom, second carbon atom. So in the second carbon atom, hydroxy group is on the right hand side in erythrose. In the triose, the hydroxy group is on the left hand side. Otherwise, what we can say that in triose, the priority groups are in the opposite direction. In erythrose, the priority groups are on the same side. And for the conversion of glyceraldehyde into erythros and threos is by employing a Kiliani-Fischer synthesis. What is Kiliani-Fischer synthesis? It is nothing but a reaction of an aldehyde with hydrogen cyanide. It will give you a cyanohydrin. That cyano is hydrolyzed to acid. Acid is esterified, and the ester is reduced to get newly formed aldehyde. Already present CHO is converted into OH. Suppose OH is coming on the right hand side, erythro is formed. If the OH is coming on the left hand side, threose is formed. Okay, once erythro is formed, so this erythros subjected to oxidation by using mild oxidizing agent. So what will happen? The aldehyde group is converted into carboxylic acid. Similarly, a primary alcohol converted into carboxylic acid. So what is the name of this compound? It's a mesotartaric acid. Why it is optically inactive? Because there is a plane polarized light is passing through the mesotartaric acid. So that is the reason it is optically inactive. And similarly, a threose, when it is subjected to oxidation, a aldehyde group as well as the primary alcohol gets converted into carboxylic acid. And here the obtained one is tartaric acid, and this moiety does not have a plane of symmetry. So both, if the plane is passing through between these two carbon atoms, so these two are different only. So but when a plane is passing through between these two carbon atoms, so this a plane bisects this molecule into two equal halos. So that is the reason this mesotartaric acid is having a plane of symmetry, and this does not have a plane of symmetry. So that is how the determination of configuration of aldotetroses. Otherwise, what yes, it's aldotetroses only. This is about okay. Now tell me, is there any doubt in determination of configuration of aldotetroses? So here we are taking glyceraldehyde subjected to Kiliani-Fischer synthesis. We are getting erythro as well as threo. The obtained erythro and threo on oxidation with nitric acid. One is erythro is giving optically inactive compound, threo is giving optically active compound. So is there any doubt in determination of configuration of aldotetroses?
No, sir.
Okay. So next I will go for aldopentoses. I will go to the next slide. Aldopentoses. So aldo means a aldehyde containing one. So how many carbon atoms are there? 1, 2, 3, 4, 5. 5 carbon atoms is there. That is the reason it's pentose. And how many chiral carbon atoms are there? 1, 2, 3. 3 chiral carbon atoms are there. Then how many isomers are possible? 2 to the power of n. That is equal to 2 to the power of 3. That is equal to 2 into 2 into 2. So 2 2s are 4, 4 2s are 8. 8 optically active isomers are possible. And all these isomers corresponds to the D and L isomers of ribose, arabinose, xylose, lixose. Ribose, arabinose, xylose, lixose. So when you are moving from aldotriose to aldotetrose, only two things, one is erythro, another one is threo. But when you are moving from aldotetrose to aldopentose, so there will be a ribose, arabinose, xylose, and lixose. So now let's go to the next slide. So look here. So this is one, I'm taking erythrose. So erythrose is nothing but a what is called as a tetrose, aldotetrose. So when I am taking a D-erythrose and subjected to Kiliani synthesis. 1 minute. Okay. Now, okay, erythrose, D-erythrose, when it is subjected to Kiliani synthesis. So what is Kiliani synthesis? Reaction of an aldehyde with hydrogen cyanide. So what will happen? Hydrogen will form a bond with oxygen, cyanide will form a bond with carbon, aldehydic carbon. So that means here Cn is coming and C double bond O is converted into OH. That is first step. And the second step, nitrile is hydrolyzed to carboxylic acid. In the third step, carboxylic acid is esterified. In the fourth step, carboxylic ester is converted into aldehyde. So that means one carbon, one aldehyde, newly constructed aldehyde is added to this carbon. Already aldehyde is converted into alcohol. Suppose alcohol is going towards the right, then it is called ribose. If the hydroxy group is going towards the left, then it is called arabinose. And suppose this carbon, second carbon, hydroxy is going on the left hand side, then it's called xylose. If the hydroxy group is going the right hand side, that I will come in the next slide. So at this moment, what you can remember, D-erythrose, when it is subjected to Kiliani synthesis, whatever the aldehyde is present, that is converted into OH. A new one more CHO group is introduced by the Kiliani method of synthesis. And in this method, if the newly formed hydroxy is going on the right hand side, then it's called ribose. Newly formed hydroxy group, if it is coming on the left hand side, then it is called arabinose. Both ribose as well as arabinose, when it is subjected to oxidation, aldehydic functional group as well as the primary alcohol converted into carboxylic acid. And here, so there is a plane of symmetry. So the plane of symmetry means it's an imaginary line passed through a center of the molecule, and if it bisects the molecule and if it gives two equal halves, then such molecule will have a plane of symmetry. So more particularly, when a line, imaginary line is passing through this carbon, so this moiety is having plane of symmetry, and this is optically inactive. And similarly, when arabinose is subjected to oxidation, it gives optically active compound because there is no plane of symmetry. So here or there. So So no plane of symmetry. That is the reason it's giving optically active a dicarboxylic acid. So with this, I will go to the next slide. So in the next slide, I am taking a triose. So triose is a tetrose. When it is subjected to Kiliani synthesis, newly formed hydroxy group is on the right hand side, then it is called xylose. Newly formed hydroxy group is on the left hand side, then it's called lixose. So both the compound, when it is subjected to oxidation, so xylose giving optically inactive because there is a plane of symmetry. So imaginary line is passing through this carbon and it bisects the molecule into two equal halves. That is the reason. So this is optically inactive, and this one is optically active because there is no plane of symmetry. So this is about what is called as determination of structure of what you call aldopentoses. Is there any doubt? Aldopentoses means ribose, okay, xylose, lexose. Any doubt up to this?
Explain optical active inactive, sir.
Optically active means a plone. So optically activity means it's nothing but a chiral compounds. Okay, chiral compounds having a characteristic property. What is that property? The optically active compound can rotate the plane polarized light either to right or left. If it is rotating right, then we can say that it's a extrarotatory. If it is rotating left, then we can say that levorotatory. But this suppose a molecule is having a plane of symmetry. So plane of symmetry means it's an imaginary line. If it passes through a molecule, if there is a formation of two equal parts, say for example, a imaginary line is passing through this carbon. So then what will happen? It bisects the molecule into a two equal halves. So that means you can see that above part is similar to the below one. So that is the reason this moiety is having optically active, and this is it won't rotate the plane polarized right, either right or left. So that is the reason this is optically inactive. So whereas this moiety, this does not have a plane of symmetry. So plane of symmetry means again a imaginary line passing through this carbon atom. If it is passing through this carbon atom, both the part. So this part as well as this part is different, and it is exhibit optically active compound. Is it clear?
Yes, sir.
Okay. I think now it's 1 o'clock. I think you have one more class now. Ashla ma'am class is there, I think. Maybe what I will do, I will stop at this stage, and I will continue in my next class. Okay.